Okay, so we are finishing up the command and data handling section today. We're going to be talking more about flight software, how to do analysis on a data budget, and avionics reliability. So for software, there are three types of software. In chronological order, the spacecraft must have ground test software, embedded flight software, and mission operations software. So as you'll remember, on the top right is a block diagram of some sample of ground test software. There's a ton of ground test software that is not just simulation or interface emulators. It can be a bunch of isolated component tests, subsystem, and system tests. And this kind of software stays on the ground. You don't upload it to, now we can move on to the embedded flight software. The embedded flight software is what actually flies, and it is as minimal as possible the software set that covers the critical functions and fault tolerance of the satellite's logic. On the right, you'll see a state transition diagram that has samples of different modes and different coded states and transitions between those modes. All of this logic is either autonomously transitioned or manually transitioned by mission operators. And so the last one, mission operations software, is the software that stays on ground during the mission. This is for mission operators to monitor and command the spacecraft. On the bottom left, that particular instantiation is the Cosmos Mission Operations and Support Tool, MOST, created by Dr. Sorensen and HSFL. So although there are three types of software, I'll only touch briefly on the ground test software, like simulation and emulators, and the mission operations software, and we'll focus on flight software. So the ground test software, a lot of it can come in the form of simulation and emulators. The point of these simulation and emulators is to replicate what the spacecraft would see or feel from the environment, to spoof measurements or to output measurements that sensors would read within the spacecraft, and to propagate orbital mechanics and attitude dynamics. On the right is a diagram built in MATLAB. It's a block diagram that shows how a simulator could work, the inner workings of a simulator. So at the very beginning, before you enter this simulation loop, you have to initialize spacecraft settings, like the spacecraft mass, moment of inertia, its initial state, like its initial orbital parameters, its initial attitude, and then sensor and actuator characteristics. All of these parameters then feed into a simulation loop where you are simulating through time. So you're updating at every step the state, which includes your orbital parameters and your attitude. This simulation loop, which actually integrates the state, informs these environment, sensor, and actuator models so that you can actually spoof the measurements that the sensors would see. But remember that this is all virtual. This is all a simulation, like in the Matrix, not an actual space environment. These simulators, this environment sensor model, will then actually feed into the prototype flight software, which is a flight software that you're testing, that you are eventually going to load onto your actual onboard computer that's going into space. By feeding it to the prototype flight software, you can test your flight software on ground and debug any bugs that are in your software, not out any kinks in the operations of the flight software. So these simulators are for testing on ground and trying to test in a way that doesn't stress the hardware, yet tests out the flight software. There are more rigorous tests where This is just software in the loop. But from the previous lecture, we've talked about hardware in the loop, where this prototype flight software is not only just flight software, that it's not only virtual, it's loaded to the onboard computer, and the interface here would be an actual physical connector, and you're running the flight software on the onboard computer. So that's one level of complexity and rigor associated with test software. So we have a question out here. Considering the mission will fail if the software misses even one integral step, if a team spent 2 years designing and building the physical hardware to go to space, how much time roughly would go into programming to make sure it was right? So I don't know the exact timeline for 2 years of designing and building, but I did look up a case study of the Mars Curiosity rover. So for context, the Mars Curiosity rover had 3.8 million lines of software, of code. That is equivalent to about 60,000 pages of text or 100 really large books. It had 2 CPUs, or central processing units, one of which was a spare. It had 120 parallel threads, and the software development time took 5 years with a team of 40 software engineers. That 5 years encompassed not only the generation of code, but also the testing of the system. So that's 5 years of software development and testing time. For actual hardware development, the dates aren't exact, but in 2004, NASA called for scientific experiments and instrument proposals. So that would mark the beginning of the hardware development, where the payloads are actually defined and you start to pick components. Testing of components also began in late 2004. And then launch was proposed for September 2009. So within that entire time, hardware and software was being developed in parallel in the 5 years. So I'm going to go back for a second. The number of software engineers, there was a team of 40. So although the software and the hardware spanned 5 years each, the hardware team probably consisted of a lot more engineers and a lot more engineering hours. So I think the foundation of this question is, what is the ratio of time spent on hardware versus software? And I don't know the exact answer for that, but significantly more time, I think, is spent on the hardware selection, fabrication, and testing. All right, mission operations interface. So here you'll see the Cosmos mission operation and support tool, but I also have the Apollo mission control center on the top right and an individual console on the bottom right. The point of a mission operations interface is to monitor various critical aspects of the spacecraft, like state of health, orbit, attitude, and also to be able to command the spacecraft, like the desired mode that you want it to be in, whether that's science operations, radio pointing, command attitude, and orbit. So the difference between the mission operations interface on the left and on the right is that the interface on the left, Cosmos, is for a small spacecraft, and this interface, all of the different subsystems could potentially be viewed on one screen. On the right, this was during the Apollo era, so one difference you can see immediately is the technology of the monitors, but you'll also see there are a ton of screens, and you can imply there are a ton of mission operators. So each mission operator is responsible for a subsystem or a component or monitoring a specific thing. Whereas on the left, you can have this architecture of one mission operator monitoring all things at once. All right, let's dig into the meat of this lecture. So, flight software. Flight software falls under the categorization of embedded software. Embedded software is loaded onto an embedded computer, and what that means is an embedded computer has no mouse, keyboard, or monitor. So unlike this laptop that I'm presenting on and this monitor that I'm also transmitting on, I'm interacting with it through a keyboard. Instead, you see a computer in the form of a board. So there's a lot of code that is loaded onto it, but how does that code get onto an embedded computer? The process is to write our flight software or code on some machine, on a Windows, Mac or Linux computer, and then we cross-compile for target processors. So that was that build action that you did when you were trying to run the Cosmos tutorial. And then you transfer this object code to the embedded computer. So that's this step here, where the compiled programs get transferred to the embedded computer. And then you can control the embedded system with a ground system. So you're doing it wirelessly or wired through some kind of umbilical cord. But typically on a spacecraft, once we load it on, once we send it to space, it is through RF transmissions. Okay, let's talk about the software architecture that actually goes on the computer. Fundamentally, the flight software must receive, transmit, manipulate, and store data from the hardware. Now, the typical software architecture, regardless of whether it's a spacecraft or a personal computer, is that you have a user layer that interfaces with an application layer, and then an operating system that interfaces with the hardware. So this is the general flow and management of data. You can also reform this diagram to be a little bit more specific, where if we look application down, your embedded computer is going to have these applications. It's going to have a kernel or operating system that interacts with the CPU or central processing unit, memory, and also various devices that are payloads or subsystem components. Let's talk a little bit about the operating system. An operating system, or the kernel, is a system software that manages computer hardware, software resources, and provides common services for computer programs. On my personal laptop, I have Windows, but on the onboard computer for Artemis, we're running Linux. The operating system keeps track of time to schedule tasks, processor time, and mass storage. The operating system interacts with the embedded hardware, like memory, and peripheral devices through input-output interfaces, like the payload. An embedded operating system utilizes real-time preemptive multitasking and is typically smaller than Windows, Mac OS, or Linux. Some real-time operating systems are VxWorks, RTEMS, and FreeRTOS. Now let's dig a little bit further. So we are talking about the operating system, but we also need to talk about the application software, the application layer. So the components of an operating system include a kernel, networking, security, and a user interface. With the aid of firmware and device drivers, the kernel provides the most basic level of control over all of the computer hardware devices. Application software, on the other hand, includes mission-specific software, which does work required by the user or the mission rather than in support of the computer. The application layer is one level of hierarchy closer to the user, so you don't have to do the nitty-gritty work of managing the hardware. Instead, you can encode logic that is relevant to the mission. So some examples of that, general comparison chart on the right, but specific to spacecraft, let's talk about the operating system responsibilities include ingesting data from the payload, then storing payload data and spacecraft state of health data, managing or coordinating the passing of data through the software pipeline, executing user commands and transition between user-dictated modes of state, whereas application software responsibility is at higher level. So this includes deciding when to conduct the science mission with the payload, deciding which sensors to be collecting from, handling mode transitions without user intervention, calculating thruster commands for orbit control. So you can see here that the application software is a higher level of functioning and the operating system is a lower level of functioning, but both are equally important. Typically, the operating system is a little bit more defined beforehand, and the application software that is more mission specific and a bit more human readable when you're developing the software. Okay, aspects of flight software that you might have to think about when you're designing a software architecture is real-time processing. For some data processing, for some maneuvers and operations, time really matters. Specifically, the keeping of time really matters. There are hard real-time and soft real-time processes where hard real-time, you are very strict about keeping time. So here we have characteristics of computer performance for hard real-time and soft real-time processes. For processes that have response time considered, a hard real-time system requires strict response time, whereas a soft real-time can fudge it a little bit. So maybe some processes to think about and to latch onto. For hard real-time, attitude dynamics and orbital dynamics may require very precise firing of thrusters or actuation, whereas soft real-time could be things that have a longer time span. So it could be the processing of payload data so that you compress it. So there's not a strict deadline for it, but it needs to be done. For processes that have peak load performance, hard real-time systems adhere to predictable processes, whereas soft real-time, it degrades the peak load performance, but it gets it done. For hard real-time systems, the control of pace is defined by the environment, whereas for soft real-time processes, the control of pace is defined by the computer. For safety critical operations, hard real-time is critical. For soft real-time, safety is non-critical. For the size of data files that hard real-time can handle small or medium files, whereas soft real-time can handle large. So I'll let you go on with the rest of the characteristics. Just intuit that there are two types of real-time systems that you have to consider for your operations. Okay, there's also a consideration of centralization. So on your spacecraft, it could be that you have a centralization of all processes, of all data coming through to one node. It could be that you distribute the amount of processing units across different boards, like having one central computer and then having daughter boards that do the intermediate processing. And then you could have a decentralized system where all the nodes are pretty much equivalent and are connected to each other without one computer commanding everything. Instead, each is connected to its neighbor and commands itself. Okay, so a couple examples of software architectures. Here I have the core flight system, which was developed by NASA Goddard. There is a version of core flight software that is out there in open source called OpenSatKit. But what I wanted to expose you to is not just Cosmos, but here is a NASA way of doing it that has been flown and has space heritage. So here you'll see some similarities between the application, kernel, and then component layer, physical device layer. Here, core flight system, or CFS, is separated into development tools and ground systems, and then an application layer, a core layer, and an abstraction library layer. So these two together can maybe be simplified into a kernel. And then you've got your hardware layer that interacts with the abstraction library layer. The application layer, you'll see there are a bunch of functions and examples of what applications can be. Here is a demo of Cosmos. So so this is a Cosmos demo in which the software has been compiled and a bunch of different agents or programs are being run. The user just brought up the mission operations support tool, and those agents are running in the background that are actually supplying the data to be displayed on MOST. So if you get Cosmos running, this is something that you could see. Oh, and there's a little demo of the Cosmos executive operator where you actually send commands. Cool. So we just talked about software. Software architectures are like the skeleton, whereas the communication architecture are like the joints that connect the skeleton together. They get all the functions to transfer data in between. So the communication architecture within software could be something like this. I'm extending the core flight system software architecture and describing it further in the communication architecture to give you a more round perspective of what software could be like. So we have a bunch of these mission applications, and these blue dots are CFS applications. We also have core services and applications, which are more on the underneath, the low-level control. All of these applications you can visualize are hooked into this software bus. And the software bus constantly has a stream of messages and data packets that are flowing on it. What I've seen is that the packets have some kind of identifier about what's contained in them, and these applications will subscribe, will always be grabbing little packets from the software bus and then looking at the identifier to see if the application wants to actually process that data. If it doesn't, then it just either sends it along in its way or gets rid of it in its own temporary memory. So if you imagine that there is a bunch of data that is constantly just flowing through and being subscribed to, some of these different nodes or applications are generating and pushing data onto this software bus. Now, we just talked about how data flows at this application layer. But to get to this application layer, we have to go through a bunch of layers from the actual devices, from the physical layer, all the way up. So from the previous slide, you'll see here that the hardware is down here and it's connected to this MIL 1553 bus support. So between here and the bus, there are standards or protocols that each packet has that moves up the chain. You'll see here where your hardware is transmitting bits, but then at the next layer, the bits get interpreted into frames. And at the next layer, the frames get interpreted into packets, and then segments, and then into data. So common physical layers include I2C, SPI, serial ports, and USB that we talked about in our I/O interfaces. The physical layer could also be the MIL standard 1553 bus protocol and the space wire protocol that we talked about before. Some examples, I think it's good to latch onto what instantiations of these layers you typically see. So if you were to interface with a web application, say on your computer, then your application layer would be a web application. Your presentation layer would be HTTP. Your session layer, I'm not familiar with 80, but your transport layer is TCP. Your network layer is Internet Protocol, IP. You'll recognize that from IP address. Your data link layer, Ethernet. Ethernet, you know, the cables. And then Cat5, the port connection on Ethernet cables. So now we're going to move up. So physical layer. Shoot, I just described this. If we break down the physical layer, what you'll see is device hardware being passed to the parent app, which is the layer just above the data link layer. It can be MIL standard 1553, space wire. Your hardware devices could be GPS, star tracker, etc. Here is a screenshot of what the hardware device could actually be outputting through the physical layer. So these are bits unto themselves shown on a oscilloscope, shown on an oscilloscope. So this is the most raw form of data that you could receive through a layer, and then it gets processed upward. The data link layer is the next layer that we care about. So we have the physical device that we just talked about. These little bits or bytes get processed into and put into a segment of the actual data packet. So these communication protocols add these headers onto the data so that when it gets sent upwards, it gets sent to the right place. there are different headers or addresses that these data packets get sent to. Data link protocols specify how devices detect and recover from collisions and may provide mechanisms to reduce or prevent them. This layer is the protocol layer that transfers data, called frames, between nodes on a network segment across the physical layer. The Ethernet 2 frame, the most common Ethernet frame format, which I have down here, actually shows how the physical device data gets wrapped up and how the header and a checksum, which prevents the checksum, helps to interpret if there are any errors in the data, if any collisions have happened. So this is the format of a data link layer. If we go upward into the network layer, then, so a common network layer is responsible for packet forwarding, including routing through intermediate routers. These protocols include CubeSat space protocol and internet protocols like IPv4. Here is an IPv4 data packet. So you'll see here that these bits get interpreted into these numbers. And I hope that you've seen IP addresses before. An IP packet has no data checksum or any other footer after the data section. So just for comparison, remember the Ethernet type frame, there's some checksum, whereas the IP communication protocol does not. Typically, the link layer encapsulates IP packets and frames. Yeah, and then passes it upward to the transport layer. The transport layer, maybe what I'll say here is that as you go up, you whittle down the amount of headers that you see on your data packets, and you actually get to the user data at the very highest layer. The transport layer, in this case, is the actual transport of the information across space. So we cover this in the satellite communications subsystem, where the data link layer transfers to a form that can be transmittable through RF. And then the actual layer is right here across space, and then it's received to a ground station. Once it's received at the ground station, the session, presentation, and application layers can be encapsulated in some mission operations interface that processes that data and presents it in a way, in a potentially visual way, for mission operators. Generally, the application layer is the scope within which applications or processes create user data and communicate this data to other applications. This final layer strips away all headers, and we are left with the actual data, which can be displayed, interpreted, and acted upon in the Mission Control Center. Okay, so I know that I fumbled through that, and apologies, but I'm going to attempt to summarize it. When we are thinking of the transfer of information from hardware, which is feeding into the physical layer, to the mission operations interface, which is the application layer, we have to go through this flow of formatting. So at the physical layer, the Artemis CubeSat kit is using SVI, I2C, UART, CSI, and then it gets processed through Ethernet, through specifically SLIP proposal, and then at the network layer, we are formatting our data to standard IP. At the transport layer, Artemis is using UDP, And then at the application and presentation and session layers, we're using the Cosmos Mission Operations Support tool. Now, all of these should already be built in for you when you're adopting the Artemis CubeSat kit, but I think it's good to understand the communication architecture in case you need to debug. The sources of error when you're testing or debugging could be at the physical layer if you don't hook something up right, or if you don't use the correct communication protocol. And when you're processing the bits, if you use a different communication protocol, then it could be that you get the wrong data. But anyway, the point of the class is to learn to understand. Okay, so let's talk about how to encode modes of operations. This would be at the application layer. What kind of applications can you write? How do you encode it? So there are different types of modes. At a very high level, your modes can be a standby mode, initial checkouts, normal mode or nominal operations, and a safe mode, where I have another state transition diagram that is more chronological. So let's walk through it. Before we launch, we can do a self-test, and then during launch, we can be in some kind of launch mode, but CubeSats are meant to be off. After orbit insertions, we can do a self-test. Now in this gray region, the bus avionics do not play a relevant role. Communication of telemetry is possible for other spacecraft. For the CubeSats, we are staying off. But after orbit insertion, 30 minutes after, we turn our computer on and we turn RF, any kind of RF transmission and receiving, that can also go on. And we can initiate a self-test. That self-test can be encoded in the flight software in some kind of intelligence of automating, turning things on, measuring if they draw the right current, and then doing that sequentially across all of your different components. And there are transitions. So exit conditions could be, if it turns out okay, then you start your on-orbit or on-station operations. If you fail, then you run error contingency, which is a layer further of intelligence where you do even more rigorous testing. You're trying to figure out what the error is. If it resolves, then you go back to your on-orbit or on-station operations. If not, then you're in failure. So the things that are active during this time, this initial checkout: power, avionics, communication, and the subsystems that are under test. And then for your on-orbit, your on-station, everything can be on at different times. And this should cover pretty much the entire life of a spacecraft. All right, so let's dig into what normal or nominal operations could look like. On the right here, I have a diagram that goes more into the detail of the code that transitions modes. So let's just talk about normal operations and then we'll dig into this diagram. Normal operations can include science operations, data uplink and downlink, spacecraft charging and sun pointing, attitude control function or orbit control function. These different normal operations assume that your spacecraft is healthy and that it can conduct mission operations as usual. So let's go into this state transition diagram. Upon launch, we enter this operation where, so one node, one state is a configuration. The arrow that goes to the next state is a state transition condition where if during this mode you have finished the launch configuration, then you move on to configure the telecommunication system and activate the sequence of telecommunications. Each of these different modes is a block of code that executes what the mode is supposed to execute. And during any point of that executable, if a condition is met to exit it, then the mode transitions to the next state or mode. You'll see there are a lot of sequential mode transitions, but there can be multiple exit conditions associated with one mode, for example. Yeah. Now you don't necessarily need to encode this in Cosmos, but I think it would be a good exercise to figure out what the modes are for your spacecraft. To draw a state transition diagram, you don't need to have the exact code or programs named out, but you can write out what the operation sequences would be and write the transitions. Think about what are the conditions to transfer from one state to another. And then we can think about encoding that state transition into actual code, which you'd have to learn Cosmos C++ to do. Okay, finally, another set of modes that I want to talk about are failures and safe mode. We talked about initial checkouts and post-launch deployment. We talked about normal nominal operations. Now let's talk about if things go wrong, there are failure detection and isolation, failure recovery, reconfigurations, and safe mode. So failure detection and isolation is within any one of your modes, you sense that something is wrong. That usually comes up in the form of if your current draw is above or below what you expect for normal operations, then you exit that mode and you go into a failure detection and isolation mode that does something similar to checkouts, but instead of just ensuring that things are going well, you report something that doesn't go well. Failure recovery is the step after failure detection, where once you've isolated a problem, then you can rectify that problem. Reconfigurations can be the uploading of new code, and safe mode can be defined differently for different missions, but typically it means go into a low power mode, go into a sun charging mode, turn off your payload. Just try to pretty much put the spacecraft in fetal position and wait until a mission operator figures out what to do next. So I have a state transition diagram here again, just so that you're comfortable with how these look. I don't think I need to review it, so I'll just idle here. I'll answer this question. The objective of safe mode is to keep the satellite in a safe state. What types of actions can the spacecraft take in order to keep the satellite in a safe state? Okay, I answered that. Low power mode, sun charging, beaconing every once in a while, turning all non-critical spacecraft functions off. Okay, so I answered some of the questions, but there were a ton of questions about hacking, so I saved that towards the end.